I hope it will be fun. So we can approach stellar evolution through three phases: pre-main sequence phase, main sequence phase, and post-main sequence phase. So let's see what happens before the main sequence. Uh, so first we need to have uh, in space there will be gas clouds. So how do you know if the gas cloud can form into a star? The gas cloud should meet certain criteria. It should be in certain situation. To know if it is ready, we need to know something about gene's mass. So gene's mass is basically the condition where the mass is not quite the stellar mass, but the mass but the mass satisfies the mass of the open cluster of stars. Uh, this temperature and density is like the relevant value for the gas clouds. And to calculate the gene's mass, you approximate mass to be rho r cubed. The total energy is the combination of the kinetic energy of the gases and the potential energy. Uh, and because we want the instability of the gas clouds, we make the total energy to be less than zero. And through that, and also we get the pi in the equation because it's there in the definition of radius of gene's radius. Even I'm not convinced about this argument, but yeah. So that's how we get the pi factor. Uh, Through this, because we know the rho and t values and rest of them are constants, we can easily calculate r, and through that we can calculate the gene's mass. Over here, you can also observe that the gene's mass depends on the temperature of the cluster. That is an important observation. To know if the cluster of gas is ready for a gravitational collapse, uh, the gravitational collapse depends on two things. Uh, so basically, initially the gas is so thin that the radiation escapes easily from the cloud. Uh, because of this, the temperature is like almost maintained in the in the gas cloud. So uh, uh, the critical mass uh, of gene's mass decreases when the cloud starts contracting, and due to this, even the density starts increasing. Uh, and because the cloud is now considered to be roughly isothermal, it kind of becomes unstable. And as you know, it's like when the gas is constricting, uh, I'm so sorry. It's like I hello.
Yes, you are audible.
Yeah. I'm so sorry. My voice is shaking. It's like I'm bad at public speaking. Uh, Yeah, so basically, because the gas is constricting, the G, the G, the gene's mass also decreases, uh, and the density increases. Because cloud is roughly isothermal, it's unstable and it causes gravitational collapse on like smaller scales. Uh, and in addition to this instability, there is another instability that's caused by rotational that is caused by angular momentum. If we consider the gas cloud to be completely isolated in space, then you can approximate the angular momentum to be like you can approximate the angular momentum to be conserved. When you're considering the gas cloud to be constricting, then the uh, angular velocity of the gas cloud keeps increasing. So when the angular velocity of the gas cloud keeps increasing, you will realize that the ratio between the acceleration due to rotation and acceleration due to gravity, that becomes inverse. That also has a inverse relation to the radius of the gas cloud, and also because the angular velocity is increasing, this ratio is also increasing. This further adds to the instability, and these processes keep repeating till the cloud of gas becomes a cloud of stellar mass. Then there is something called hydrostatic contraction. Uh, so when the star is in approximate hydrostatic equilibrium, uh, we consider the virial theorem to somewhat to be satisfied, uh, and uh, and to reach the hydrostatic equilibrium, first the stellar mass should go from isothermal to adiabatic. Over here, uh, in isothermal, it's unstable because uh, uh, you know the pressure the pressure is unable to keep up with the gravitational gravitational potential of the collapsing mass. As you can see over here, uh, it's just r to the power of 4 here. Oh wait, I think it's just r to the power of 4 here. I have to change this a bit. But when it comes to adiabatic, then the p depends on the relation between p and r changes because p depends on density by 5 to the power of 3. And when you substitute it like that, you see it'll be 5 to the power of uh, r to the power of 6. It's not 4. It's my error. And this is you can and the gas clouds change from isothermal to adiabatic because when it keeps contracting, the gas clouds become more opaque as they get denser. Thus the radiative energy uh, that goes outward is contained back in, so there is not much exchange of energy. Thus it turns adiabatic. And then to understand the evolution, you must know about the Hayashi Track. Hayashi Track is basically luminosity and temperature relationship. So stars between around 0.5 and below, they okay wait, we can go from 0.1 to 3. They have like this radiative zone. They usually have like this radiative zone before they reach the main sequence because they're like small mass stars, uh, and more than that, from 3 to 10, they have like they're like already fully radiative before they reach the pre-main sequence stage. And heavy stars, they're born into the main sequence. And some huge stars, they don't even have to go through the pre-main sequence stage. They just are completely ready. Yeah, so basically, as these stars contract, there is like a decrease in luminosity because the surface area through which the radiative, by which the light that is emitted is less. So, thus the Hayashi track gives the change in luminosity with respect to the surface temperature. You can see that the change in surface temperature is nothing when compared to the change in luminosity. In Hayashi track, we assume a star is fully convective. This is kind of a good approximation for a newly formed star because it's still in the pre-main sequence stage, and that cool and like they're highly opaque, so radiative transport can be ignored. And if you consider yeah, uh, and when the star leaves the Hayashi track, it experiences a sudden increase in temperature. This rapid increase in temperature happens in the Hayashi track, uh, and finally the temperature reaches a point where it's high enough for the hydrogen in the core of the star to start burning, and that is when it enters the main sequence. The main sequence is basically when the hydrogen in the core is burning. And also towards the right of the Hayashi track, it's like the forbidden zone. You cannot have a model of a star at such low with such low surface temperature value. If you try to construct such a model, then the core of the star will be void. So basically, the contraction of the star stops when burning of the core begins. Huh? This is a Hertzsprung-Russell diagram. This is also one of the most important thing to identify and categorize stars. This is basically a graph between luminosity and temperature. It is not exactly temperature. Some say spectral class. Some say stellar color. Against the color is in quotes. So basically, you assign a color in quotes again, to a star based on what temperature range it lies in. Uh, if we consider sun, it is considered to be in G2 spectral class, so its its temperature is going to be between 5,000 and 6,000 Kelvin. And this is how you read the uh, HR diagram. Towards the left top, all the stellar masses will be hot and bright. Right top, will be cool and bright. And left down is hot and dim, and right down is cool and dim. This is like simplification of it. And then now we can see what happens in the main sequence stage. There is something called as zero age main sequence ZAMS. This is when like the hydrogen burning has just started. So basically, uh, yeah. So in main sequence, there's a tendency that all masses, the luminosity of all masses increase because of central burning of hydrogen. As hydrogen is converted into helium, the abundance of hydrogen in the core keeps decreasing. You can't deny that. But this decrease in abundance of hydrogen also increases the mean molecular weight at the core, and that in turn affects the pressure. Yeah, it's easy to arrive at. You can understand this equation through this. This is basically the partial pressure, uh, and the total pressure will be the sum of all the partial pressures, and uh, rho and xj is the abundance of the jth element. This is just a general thing. So and aj is like the atomic mass, mu is the atomic mass unit. Uh, so you can figure out the number of atoms per unit volume, and then the total number of ionized particles is basically there is Zj number of electrons. Zj is basically uh, Zj is basically the atomic number. So those many number of electrons will be there, and that one is attributed to the nucleus. And so combined, and is there something? Huh. So basically, combining those two, you can find out the number density, and through that, you can calculate the total pressure. And basically, this contraction of this core again releases a lot of gravitational potential energy. And I think in the last lecture, last session, Virial theorem was introduced, and because of the Virial theorem states the uh, connection between internal energy, total energy, and thermal energy. So basically, because gravitational potential energy is released, the the part of the gravitational potential energy goes into the internal energy, because of which the temperature increases. And when the temperature increases, obviously the nuclear energy increases, which causes like more nuclear reactions to happen, and then this just continues on. This is kind of why main sequence reaction takes place for a very long time. Yeah. Uh, and because of the luminosity of the star also keeps increasing as the radiative flux of energy increases when temperature increases. And I think I think there is another equations you guys must be familiar with. The luminosity depends on 4 pi r square into uh, Stephen's constant into effective temperature to the power of 4. Yeah, so you can also see like the comparison between low mass and expansion and high mass expansion. For low mass, the expansion is like kind of noticeable but not too drastic, and the increase in luminosity leads to an increase in effective temperature. It follows that equation I just said. But if when you go to the higher mass, the expansion is much more rapid, but the effective temperature decreases. Uh, there is still no reasonable explanation for this phenomenon, but one of the convincing argument was put forth by Douglas Core. He, in his unpublished set of lecture notes, he argued that the Virial theorem is not just about the core of the star. He says that the Virial theorem applies to the entire of the star. So basically, when there is basically the total thermal energy does not just apply to the core; it applies to the entire star. So instead, if you just change the okay, if the entire energy just goes to the core and the temperature uh, and the temperature changes just because of that, then the temperature increase is like so drastic that it causes the core to be degenerate. uh, so it will be extremely unstable. For this To make sure that this doesn't happen, uh, when the core contracts, the outer layers of around the core, it expands, and through this, it's like the temperature is not completely focused on the core, and there is just enough temperature in the core for the nuclear reactions to take place. This is extremely important because in high mass stars there's something called the Cno cycles. It's basically this Cno cycle is extremely temperature sensitive. We'll come to Cno cycles eventually. So what happens after main sequence? So now the stars exit the main sequence only when the hydrogen in the core is completely exhausted. Uh, when there is no hydrogen left, we can conclude that all the hydrogen has converted into helium, and with there might be even small traces of other heavy elements. And for helium burning to take place, we need a very high temperature. The temperature should be around 10 power 8 Kelvin approximately. But at this moment, the star need not have that temperature. Uh, so this star need not have that temperature. So this so to get to that temperature, we need energy. So the the core starts contracting till there is enough energy for. Oh, before that, I should also mention, uh, though there is no hydrogen in the core, there is a small blanket of hydrogen that surrounds the core. That's called the hydrogen shell. So there is enough temperature for the hydrogen shell to start burning. So when this hydrogen shell starts burning, there is enough that slowly causes rise in temperature, and the core also contracts to just reach the point where the helium can ignite and burn. This uh, yeah, so this also increases the thermal energy of the core, which causes like the helium to burn. And when helium is exhausted, then it goes on to other elements. Helium will give rise to carbon and oxygen, and this carbon and oxygen, they give rise to other elements, which I don't know if I have that cycle here. Okay, this is the Sienna cycle. Okay, so it is kind of like a. So it is like cyclic. So when there is carbon and oxygen, there won't be enough. The temperature won't be enough for that to burn. So the helium again, helium shell ignites, and it causes the carbon and oxygen to burn, and it keeps going on depending on the mass of the star. The mass of the star will determine when it cuts off. Yeah. Then we can go specifically to a moderate mass. Okay, basically proton chain reaction is conversion of hydrogen to helium. A proton hits hydrogen and it forms deuterium, and with the help of another proton, it forms tritium, and then finally the conversion to helium is completed. With like a release of two positrons and neutrinos. And this is basically helium burning, which leads to carbon. And carbon, when it combines with four with helium, gives rise to oxygen, and this goes on. And this is the Cno cycle. The Cno cycle only happens in heavy mass stars. This is like a evolutionary track of a moderately mass star. So in a moderate mass stars, it has a convective core. Yeah, and hydrogen is exhausted in the core. So initially, it's like it follows the same pattern as I told you. So the hydrogen shell has to burn to provide just enough, so that the temperature increases just enough for the helium to burn, and so when the helium is burnt, there is like overall contraction, and there is a increase in mean molecular mass again. uh, and all of the energy of the star is basically due to nuclear burning. Uh, and Stromberg and Chandrasekhar limit. Huh? Yeah. So basically, uh, when the star is about to leave the main sequence, the mass of the helium core, whatever that is there now, it should be like very similar to how it is when it entered the main sequence. And that mass, whatever, is very close to this thing called Stromberg Chandrasekhar limit. Uh, so, base, the growth of the core during shell burning, uh, it has to hit this. It has when if it exceeds this limit, then it essentially starts on like this. Starts moving towards this. It starts moving backwards to the Hayashi track. Uh, uh, just as how it came from the Hayashi track to the main sequence. So basically the core contraction and expansion of the surface uh, uh, keeps happening till like the helium burning is like kind of efficient in producing the required energy. uh, and the hydrogen for a moderately mass star, the hydrogen shell is like not completely used up yet. It is still active and it also contributes a lot to the energy produced by the star. And there is also something as like the shell burning law. Uh, Basically, shell burning law says that when if the core contracts, uh, then the outer layers around the core expands, and if the core expands, the outer layers around the core contracts. So yeah, and the Hayashi Track stage one is just after the helium burning starts. And when the helium burning is like completely stable, then the contraction and contraction of the outer layers and uh, uh, no outer layers expand. Yeah, the contractions of the core and the expansion of the outer layers, they stop, and the star now go through like this uh, weird. They go through another main sequence stage of the helium burning phase, and this helium is now converted into carbon and oxygen. Uh, this carbon and oxygen, they increase the mean molecular weight of the core again. So once the helium is exhausted in the core, it goes through the same crisis as it did with the hydrogen. So there is just enough temperature for the helium shell now to burn, and when the helium shell burns, uh, it has to supply enough energy for carbon and oxygen. But because the mass is just moderate, the core will become degenerate even before reaching the sufficient temperature. So basically, the temperature will drop before like the carbon ignites. So after the helium shell burning happens, the direction of evolution is like goes backwards again, and it moves up another Hayashi track. Uh, this hap- this happens because like there is like a hydrogen shell now and even a helium shell. These two expand so much that the temperature in which the hydrogen burning shell decreases to the point where like the shell is extinguished and the star only has one shell source now, which is the helium shell, and the core keeps contracting because the outer layers are expanding, and hence the effective temperature of the overall star decreases. Then there is this is like the Hayashi track stage 2. Then there is something called the asymptotic branch change. So basically, after all this, the star develops like a deep convective envelope. Uh, all the layers like have undergone some mixing, so it's like it is no, it's all elements are everywhere now. So this is like the right time to see study what composition was in the core. Uh, so this gives us a rough idea during this stage. Distribution of abundance of elements is like uh, it is like the most important clue. The luminosity of the star during this time increases greatly along with the radius. This is uh, again we do not know the reason why. It was probably because of the increase in radius that the luminosity increases. So eventually, it's like the radius keeps increasing till it forms something called the planetary nebula, and this planetary nebula it cools down gradually till it forms the white dwarf. This again takes thousands of years. And if we consider the low mass stars, we need to see how different. We can start by comparing how different it is from the moderate mass stars. These low mass stars don't even have a convective core during the main sequence stage. So by the time uh, all the hydrogen core is like burnt up, uh, the hydro by the time all the hydrogen in the core is like used up, uh, then it goes on to the shell, burning of the hydrogen shell. This hydrogen shell is like pretty thick when compared to uh, other mass stars. This shell is like almost to the center itself. So basically, before the helium, while the helium core keeps growing, the hydrogen in the shell keeps getting consumed. Over here, the Schoenberg-Chandrasekhar limit, you can't exactly calculate the accurate value. Uh, Therefore, it's like we need to see like the time scale of evolution. The moderate mass star, it followed like thermal time scale, which means it was the evolution was like very dependent on the evolution was very dependent on the temperature of this core. And over here, the evolution is much dependent on the nuclear burning. So by the time the by the time the core mass of helium the core mass of the helium has already exceeded the Schoenberg-Chandrasekhar limit. So the core is like very close to degeneracy after the. So basically, when you come to the low mass stars, I forgot to even mention the hydrogen shell is like completely used by the time it comes to the helium core burning. So by the time it comes to the helium core burning, the Schoenberg-Chandrasekhar limit is already reached. So the density of the core is like much higher, and the core is close to degeneracy. So yeah, it keeps. So there is also a slight change in the luminosity in the outer layer because of like the expansion of the outer layers and like the contraction of the core because of the helium burning. And as like this contraction continues, it goes through Hayashi track 1. Uh, And because it's like a very small star, the onset of degeneracy of the core has like already been established. It will no longer be heated by like whatever the contraction that is like fueling the thermal energy, by the contraction that usually used to fuel the thermal energy. So when the temperature reaches like the helium burning state, uh, then it is like a sudden thing. It is not as gradual as like the moderate mass level star. So this sudden thing causes like something called as the helium flash. Uh, so it's like the helium burning starts so drastically. Uh, when helium burning reaches like an equilibrium, and it goes into this helium main sequence, and finally after like the helium core is like exhausted, it goes back up the Hayashi track again and reaches like the asymptotic giant branch, uh, similar to the moderately massed star, and it forms a planetary nebula again and a white dwarf after cooling. And the sun is also like one of the low mass stars, so this is exactly what will happen to the sun. And now this is the evolution of heavy mass stars. So we need to see how the heavy mass stars is like different from low mass stars and moderately mass stars. So these stars have uh, these stars go till like carbon burning before they even reach the core degeneracy. Uh, so the core keeps getting smaller and smaller till it goes through the helium burning phase. And like after helium is like exhausted, helium shell gets burnt and then finally reaches the carbon, and the carbon uh, and the carbon core is also like goes through the burning phase. uh, and uh, and finally this continues on till uh, some heavy metal is reached. You and if in this okay, there is something called a supernova explosion. So basically, when the core when it's like an iron core, the it all this like contraction and like shell burning can never increase the temperature high enough for the core to burn again. So that is when it suddenly stops all nuclear reaction. This sends a shock wave called the supernova explosion. And because of like all these chemical reactions, there are like multiple neutrino nucleon electron interactions in the outer surface, and this neutrino nucleon interactions they uh, transfer all the energy that has been dissociated due to shock. uh, and this shock and while transferring the energy, it creates some uh, it creates some heating. So this is called the this heating basically produces enough like energy to like and propel like all some particles out of the star itself. So it's like a pretty huge amount of heat. This is like called the delayed supernova mechanism. So after like all the materials are like completely thrown away from the star, there is like this core that is left and some like leftover particles. These things come together and start cooling. This forms like a neutron star. Or if it's like very very if this is like a very very heavy star, then it might end up like forming a black hole. And basically, all the materials that are propelled by the supernova delayed supernova mechanism, those go ahead and become part of like the gas cloud, and they continue the cycle of like formation of new stars. That is basically the cosmic cycle. Yeah, the Stephen's constant is, yeah, that was the.
Yeah, so Viraja, I think you
Yeah,
have ended, right?
yeah, yeah.
Yeah, so guys, if you have any kind of questions, you can now unmute and ask the speaker. I guess I'm audible, right?
Yeah, yeah.
Okay, so are there any questions or okay? In case there are none, I want to thank Viraja for like this talk, and I mean, I personally like the talk, and the next talk will be given by Anand, and you will be notified soon regarding that. So I guess if there are no more questions, we can wind up. Thank you, Virja.
Thank you.